Hello everyone, I'm Sneha Pandit from Rosalind Center for Solar Physics from the University of Oslo, and my topic is formation of activity indicators in 3D model atmosphere. We use ALMA observatory, and ALMA has 62 antennas. Most of them are 12 meter in diameter, and separate single dish antennas for total power maps. And so far the wavelength range traces the chromosphere. The wavelength range is 3 millimeters to 0.3 millimeters, and the feed that we want to use from ALMA is the imaging of sun and other stars from the same instrument. To illustrate our observations of the sun, this is a total power map or a full disk map of the sun, and it is scanned by the single antenna. So this can be used for the reference brightness temperatures for the interferometric data. This interferometric data is from the same time, so the reference brightness temperature is used to calibrate the interferometric data, and we can see small features as well. These images are formed with salsa pipeline, which is made in-house in ROX. So this is the link that you can use to access the images or data. These are the illustrations for stellar observation. So the stars are well resolved. So the binary of Alpha Centauri, which is 4 arc seconds apart, it is very well resolved in the band 7. And another example, Alpha CMA or Sirius A from Mohan et al. 2021. So these are from band 3, 4, and 5. From the same study, we can see that for these are the observations from different observatories, and then the black line is from a Phoenix model, which is one-dimensional LTE stellar model atmosphere, and that atmosphere is without chromosphere. So this black line is from spectra generated from Phoenix model, and the red line is black body models fit taken from Sobiran et al. And this bottom panel, delta S by S mod, is basically delta S S observed, that is the fit for these observations for each point, minus the spectral flux density S for the Phoenix model, and it is normalized with the Phoenix model. So this is the variation that we see in our delta S by S mod. Now, if we see these band 6 and band 7 observations from the same paper, for example, I, G, and F, these were the 13 stars in our study. And for example, I is a K-type star, G is a G-type star, and F is a F-type star. And these three have more or less similar delta S by S mod. So since we don't have chromospheric contribution in our Phoenix model, delta S by S mod kind of accounts for chromospheric flux. So this should show differences in F, G, and K type stars, but it is not showing significant differences. Whereas in the case of band 6, if we see the temperatures, the brightness temperatures, these three are well resolved. This is just to illustrate how millimeter wavelengths can be used in the case of activity indicators. Now, since we have for our sun ALMA band 6.3 and from SDO AIA channels and H alpha, calcium 2K, and HMI continuum, the question that I put is, can millimeter continuum be used to construct better activity indicators? Now, in my study, I've used 3D model Bifrost from in-house in the Rosalind Center for Solar Physics. It is a model which has quiet sun background and magnetic loops on top of it. It is 24 megameters by 24 megameters in horizontal directions, and it goes 2.4 megameters inside the photosphere and 14.4 megameters above the photosphere. Now, if we see this movie, this is temperature and this is absolute magnetic field. We see first the loop, then the magnetic foot points, and eventually the photospheric granulation. The resolution is 48 kilometers in horizontal direction. And I have used snapshot number 1000 in my study. Now, using this model and the radiative transfer code RH, I have calculated spectra for calcium to HK and infrared triplet lines. So the gray lines behind, those are the reference line, and the black line is the filter. So the filter for K line is of the intensity of the continuum, but for H it is half the intensity, and this is how the S index is defined traditionally. We'll come to that, but for this reference run it takes more than 3.5 hours for just one column. And in the Bifrost model we have 504 into 504, that is 250,000 plus columns. So to run it for the whole simulation box, it is computationally very expensive. Instead, since we know our filters and to have S index calculated within 1% error, I have constructed another grid with red dots, with which we have calculated the whole spectra for the whole simulation box. So to see, the differences between the spectra are very negligible. You can pause the video anytime and have a closer look, but we'll move ahead. Using this line, this is K line, this is H line, we see how the atmosphere changes. So basically we start from the wing, which is formed in the photosphere, then the core, which is formed in the chromosphere, and again to the wing. So the core shows the magnetic foot points in both the cases, and photosphere shows the granulation. So now would be the time to talk about activity indices. So the first definition was from Vaughan et al. In 1978. It was observational definition. So the filter sensitivities and instrumentation was taken into account while forming the definition. Fx is basically flux, integrated flux over the filter. So if it is H, it is the small triangular filter. For K, it is the bigger triangular filter. And for V and R, it is a rectangular filter. Similarly, for calcium triplet as well, these are all are rectangular filters. And in the definition, the alpha was according to the instrument at that time, but it is in our study we have used alpha to be compatible with Soumya et al. From 2021, and these definitions are from Marsden et al. So after calculating the integrated flux for each column, we obviously expect for V and R to see granulation from the photosphere. For K and H, we see the magnetic foot points and we do not see the loops. So when we calculate S index based on these integrated fluxes, we see something like that. Keep in mind that the color scale is inverse. So the darker the color scale, higher is the S index. In the S index, we see the magnetic foot points here. And if we do more statistics, basically in this image, I have truncated the color bar at 1. So we see the smaller features which were washed out because of the color scale in the previous slide. But we see more of photospheric contribution. We see granular structures in S index as well. And obviously we see very dark magnetic foot points. Now in this histogram, basically for V and R integrated flux, we see two clear peaks, one which is broad, so that is for the granules which has higher intensity, and another which is narrower in comparison to this one. It is for intergranular lanes, it has lower intensity. In the case of H and K integrated flux, since our model is mostly quiet sun, even if we have magnetic foot points, the columns or the pixels in S index which represent that are comparatively very small in number. We see majorly the contribution from the quiet sun, and then we see a tail which shows the more active pixels, and they are less and less in number. I've also plotted the VAL, F, and D models for reference. F is the most active quiet sun model, and D is lesser than F, but still somewhat active quiet sun model. And they also show that HK flux in the integrated HK flux is more in case of the active model, whereas it's less in the case of less active model. Now, in this case, we also have done a little bit of active versus quiet statistics. So this is the top magnetic foot point, and the quiet sun is just from the right hand upper corner of the model. So the scale varies. So for active, the S index goes till 5 and above, but for the quiet case, it goes till 1, and most of the part is very dark. Now, this background, pink red background contours are for the whole simulation box, and the green is for the active uh, chosen box, and the black lines are for the quiet box. So the trend is basically that the H plus K integrated flux, it is on an average the contours shift towards the higher side, whereas in the case of quiet sun they shift towards the lower side, and the peaks are also similarly shifted. But in the case of V plus R integrated flux, they do not change much. So basically, H plus K shows us the chromospheric contribution, but V plus R is photospheric, and it is constant for active or quiet. We have done similar thing for infrared triplet index. This is the definition, and V plus R, V and R bands are basically photospheric granulation. And in the 3 lines, we see the magnetic loops, the foot points of the loops. And in the index as well, we see those loops, but we also see the photospheric contribution. Now, to compare these classical indicators with our millimeter indicators, we have this ART code. It is also in-house to ROX, which is ALMA radiative transfer pipeline. So if we put Bifrost model, that is also in-house, into the pipeline, we get millimeter fluxes, and this is just for reference. It is at 0.83 megameters. We see the magnetic foot points in the model, and we see the loops in our millimeter observations, synthetic observations, whereas in H and K we do not see the loops, and it's in S index we see the foot points in addition to the photospheric granulation. Now, if we compare these statistically, basically these contours, purple in color, are of very low frequency. Like we see less counts in these contours, whereas as we go inside in the green yellow contours, the intensity is very high. The frequency of occurrence for ALMA versus S index is very high. So the S index doesn't vary much. It is from 0.1 ish to 0.5 ish in the most of the occurrences, whereas the brightness temperature shows variation. This is band 6, where we see less temperature in comparison to band 3. And if we compare similarly in the previous case, like the active and quiet regions, for band 6 and band 3, we see some features. So basically this is active region for band 3, where the highest temperature goes beyond 12,000 Kelvin. Band 3, it goes beyond 20,000 Kelvin in the active case, where the S index varies, goes highest till 5 plus. In the quiet case for band 3, the variation is from 4,000 till 9,000, whereas in the case of band 3, it is also from 6,000 to 9,000, and the S index varies from 0.5 to maximum 2, which is a very less amount of pixels. We see ALMA brightness temperature versus S index plot here. So the brightness temperatures in goes from like 6 to 8 kilokelvin in the case of band 6, and in the case of band 3 it goes from 8 to 10, there is a variation, whereas the S index doesn't vary much. In the quiet region as well, in the quiet case, S index doesn't vary much, and there is variation in the case of ALMA brightness temperatures. So the key takeaway is basically millimeter intensities resolve the active regions from quiet ones better than the S index. Millimeter intensities also reflect the magnetic structure that we see, and it is also represented in the calcium 2 H and K. We know that S index is not solely chromospheric activity indicator, and it shows more photospheric remnants as well. And that's why we conclude that more robust activity indicators can be constructed using millimeter spectra.